And as examples, I'll add some of that as we go. So action potential travels down motor neuron, reaching axon terminal. So everything's cause and effect. So that leads to what? Causes what? Causes voltage-gated calcium channels to open. So I'll do my little plus sign for causes, triggers. Voltage-gated calcium channels, lots of shorthand, to open. So whenever you talk about a channel opening, that should immediately be followed by what's going through it. This results in calcium influx, right? Because calcium is entering the axon terminal. Why is it going in?
Because the electrochemical gradient.
It's moving down its electrochemical gradient. So now you've got calcium levels increasing in the axon terminal. This triggers movement or mobilization of
Synaptic vesicles.
And let's see, stimulate mobilization of synaptic vesicles. Yeah, toward the
Synaptic cleft. Right?
So I mean, you could say to the axon terminal membrane that faces the motor end plate, but there's an easier way to do that. Presynaptic membrane.
Okay.
The presynaptic membrane is the part of the neuron that's facing the postsynaptic membrane, right? The membrane of the target cell, where the two membranes are really close together at the synapse. Okay, so stimulates movement, mobilization of the synaptic vesicles. They move towards the presynaptic membrane, fusing with it, and releasing ACH via exocytosis. So what does the ACH do now that it's been released? Diffuses across across the synaptic cleft toward
The motor end plate.
the post-synaptic membrane, which is the motor end plate. So we've identified all three parts of the synapse: presynaptic membrane, postsynaptic membrane, and the synaptic cleft between them. So when he gets there, ACH binds to
ACH receptors.
ACH receptors. So here's an opportunity to add a little side note. ACH receptors and ligand-gated cation channels are parts of the same integral protein. Right, it's one protein in the membrane. 99% of it is a channel, but then there's that small portion on the exterior surface that functions as a receptor. So when we talk about the steps, it appears as though the receptor and the channel are two distinct separate entities, but they're really not. They're two parts of one protein. So ACH binds to ACH receptors, triggering opening of the non-selective, or we can start with ligand-gated, that's fine. Ligand-gated non-selective cation channels. So what are you going to follow that with? Just open the channel, so the next thing you're going to discuss is what goes through it. So this leads to sodium influx and
Potassium efflux.
potassium efflux. And how do they compare? Are they the same?
No.
What's greater?
Sodium influx.
So it leads to sodium influx that's much greater than the potassium efflux. Resulting in
Depolarization.
of what's getting depolarized? But we don't call it the sarcolemma. Not yet. This is the part that's folded. It's
Junctional folds.
motor end plate. Depolarization of the motor end plate, called a end plate potential. So there's lots we could add here. Let's start with the sodium influx being greater than the potassium efflux. Why is that? Sodium's electrochemical gradient is way stronger than potassium's electrochemical gradient. How do we know that? Because the voltage of the membrane at rest, which it is right now, is really close to, really far from. How do we know that the ECG is really strong for sodium and really weak for potassium right now? What about it? Because the VM is far from what? From sodium's equilibrium potential. And we can mention the value. It's plus 65 millivolts. And the VM is currently minus 85 millivolts, right? It's far from the equilibrium potential for sodium, plus 65, but really close to what? Potassium's equilibrium potential, which is minus 94 millivolts. So minus 85, really close to minus 94, but really far from plus 65. The closer you are to an ion's equilibrium potential, the weaker the electrochemical gradient. The further you are, the stronger. So we're about 14 times further from sodium's than we are from potassium's, right? 140 millivolts away from sodium, about 10 millivolts away from potassium. So you can assume 14 times more sodium is coming in than potassium is going out. This is why depolarization is the net result. How about the motor end plate? So structurally, how is it different than the sarcolemma? MEP has junctional folds, and the purpose of them? Increase surface area to house more proteins, which we're using as ACH receptors and ligand-gated channels. So ACH binds to ACH receptors, but we don't want ACH to keep stimulating, binding to and stimulating ACH receptors, or else the muscle will just keep contracting indefinitely. So what's present on that motor end plate to make sure this doesn't happen?
Acetylcholinesterase.
Acetylcholinesterase
Breaks down the acetylcholine.
ACH into acetic acid and choline. And the choline is taken back up into the axon terminal, recombined with acetic acid to reform ACH. So this is done to end the signal to contract. So what if we want to keep contracting that muscle? What do we need to do? Knowing that the neurotransmitter we just released is going to get broken down. There's nothing we can do about that. That's going to happen. Just got to keep releasing neurotransmitter, which means you got to keep sending action potentials down the motor neuron. So you keep sending the signals. All right, next. So we have depolarization of the motor end plate, called an EPP. So the EPP spreads to the, so what surrounds the motor end plate? Just your regular old sarcolemma. EPP spreads to the surrounding sarcolemma, where it triggers opening of voltage-gated sodium channels, followed by opening of, about a half to 1 millisecond later, what opens?
Potassium.
Voltage-gated potassium channels. This leads to, so you open the voltage-gated sodium channels, resulting in sodium influx, followed by, then we open the voltage-gated potassium channel, so the sodium influx is followed by potassium efflux. The sodium influx leads to what phase? Depolarization. Followed by see the pattern? The parentheses is what's going on with potassium. Prior to that, we're doing sodium. So we open sodium channels, then potassium, sodium influx, followed by potassium efflux, depolarization, followed by
Repolarization.
repolarization. which is called in. So we're at rest, and then we get this rapid dipole. We peak, repole, pass rest, hyperpole. Now we're back to rest. What's this whole thing called? This is a graph of an action potential. Just, there we go. Just to keep it going. Okay. The action potential does not literally move down the sarcolemma and down the T-tubules. It's propagated, it's regenerated. So what's really happening is we can take the sarcolemma and break it up into sections. And then we'll just start at the beginning of the sarcolemma where it's right next to the motor end plate. And we just opened our first batch of voltage-gated sodium channels, right? So sodium comes in and it spreads to the left and it spreads to the right. And as it spreads to the right, it depolarizes this piece of membrane, opening these voltage-gated sodium channels, right? So we just regenerated the action potential next door. And then that wave of depolarization stimulates the next batch of channels, right? And this is how propagation works, right? Sodium, sodium, sodium. So we get these sodium currents, right? Traveling across the membrane over and over and over again. So this just goes all the way down the sarcolemma, T-tubules, and so on. So once we get to the T-tubule membrane, what happens? So the AP spreads, or is propagated technically, across the entire sarcolemma, down all the T-tubules. So when we depolarize the T-tubule membrane, what happens?
The voltage sensitive proteins change shape.
Yep. So we have our triads here, right? We have terminal cisterna, T-tubule. T-tubule proteins change shape. They're connected to the calcium release channels, and they pull them open. So triggers voltage sensitive T-tubule proteins. In your book, they're DHP receptors. To change, delta sign means change shape, and pull open calcium release channels. So now you're starting to let a little bit of calcium out of the SR, but we're only pulling open the calcium release channels in the triads, in the TC membrane that's facing the T-tubule. You still have release channels everywhere else in the SR. So how do you get the rest of them open? So this results in calcium release. This calcium can bind to ryanodine receptors on other calcium release channels to open them. And this is called calcium-induced calcium release. And then we get a huge increase in cytosolic, or you could say myoplasmic calcium concentration. So what is this calcium-induced calcium release? As a little side note, it's an example of positive feedback. So very quickly, over the course of a few milliseconds, all the calcium is dumped out. Tons of free calcium available. What does it do?
Send it to cytosol.
Binds to
Troponin.
what part?
The
TNC. So TN is troponin, C calcium. Right, it's one of the three subunits. So as a little aside, you could say troponin has quaternary structure with three subunits. And you could go on to talk about what they are. TNC binds to calcium. TNI is bound to actin. TNT is bound to tropomyosin. And then the binding of calcium to the TNC subunit of troponin leads to triggers, causes troponin to change shape and pull
tropomyosin away from the myosin binding site.
right? Pull tropomyosin out of its inhibitory position, exposing what?
Myosin binding sites.
Exposing the myosin binding sites on actin. As soon as they're exposed, what happens? Cross bridge forms as myosin head attaches or binds to actin. So we've got our cross bridge. So we did events at the neuromuscular junction. We did EC coupling. What's next? Cross bridge cycling. So as soon as you form the cross bridge, what is the very next step? Inorganic phosphate detaches, dissociates from what? What part? What specifically on the myosin head? Let's be as specific as possible. Attaches from myosin ATPase, which is on the myosin head. And that triggers next. ADP released from myosin ATPase. Then okay. Now we we have an available myosin ATPase that ATP can bind to.
It causes the myosin head to detach.
Triggers detachment of cross bridge, or you could say detachment of the myosin head from actin. So that ATP really has two roles. That's one, detachment of the cross bridge. Two, it's ATP in the end. What's its purpose? Provide energy for something.
So it recocks the myosin head.
Has to get hydrolyzed.
Okay, okay.
Okay. ATP hydrolyzed into ADP plus PI plus energy. And the energy is used to recock, re-energize myosin head. What's next? I know we just finished one full cycle, but what would be the very next thing? Oh, I don't need to write it again. I've already written it. I'll just draw an arrow to it. PI comes off, yeah? This keeps repeating. Right, that's cross-bridge cycling. As long as we have calcium available and ATP available, this will keep going.